Hello and welcome to The Space Above Us. Episode 99, Space Shuttle Flight 29, STS-30, the spare part spacecraft. Last time, we talked about the 8th flight of Space Shuttle Discovery, STS-29. We sent a new TDRS satellite on its way, futzed around with some heat pipes, and had a fun time digging around in the oral histories. Oh, and on that note, several of you reached out to say that you were enjoying the oral histories, so you can expect more of them in the future. The STS-29 crew was anxious to get the mission underway, since if they didn't launch soon, the next mission would take priority and they would be forced to roll back to the VAB. The shuttle had 2 launch pads, 39A and 39B, but 39A was being modified, so 39B was the only option. Well, the next mission is now this mission, STS-30. So let's learn about what gave it the right to potentially give Discovery the boot. You could say that for this, the 4th flight of Space Shuttle Atlantis, the planets aligned for the mission. Well, 2 planets. And they didn't so much align for the mission as much as the mission patiently waited for them to align on their own. But that's all beside the point. STS-30 would take launch priority because it was the first of, by my count, only 3 shuttle missions to deploy an interplanetary spacecraft. Launching things to other planets is a delicate business that can only be done during limited time windows when everything is lined up just right. And if you miss that chance, you have to wait for everything to line up again. So, since STS-30 had a limited window and STS-29 could deploy a TDRS any old time, STS-30 got priority. So, it's a good thing that STS-29 got moving when it did. Interplanetary. That's pretty exciting. I don't get to talk about interplanetary stuff very often. So, where are we going? Mars? Jupiter? Saturn? No, we're heading in the other direction. Venus. These days, poor Venus doesn't get much love from NASA. In fact, the probe we'll be talking about today was NASA's second of only, at the time of this writing, 2 Venus orbiters. Magellan. Magellan was named in honor of the Portuguese explorer Ferdinand Magellan, who was the first person to lead an expedition to circumnavigate the globe. Well, mostly. He had a bit of a disagreement with some of the locals along the way and was unable to complete the journey himself. But the crew finished it for him. Well, what was left of them. Around 270 men left, and around 19 came back, so it didn't go super great, and, well, I'm getting all caught up in the wrong Magellan. The point is that Magellan expanded the envelope of what was possible with a remarkable navigation feat, and it was hoped that our Magellan could achieve a similar success. Magellan, and from now on that's just going to refer to the mission, not poor old Ferdinand, was especially exciting since it was the first time since the July 1979 launch of Voyager 2 that NASA was sending a probe out beyond Earth's orbit. 10 years is a long time to not launch any probes, but it wasn't for lack of trying. Originally, a spacecraft called the Venus Orbiting Imaging Radar was in the works, intended for a launch in 1981. It had a lot of capability, but also cost about $2 billion in 2020 dollars, so it was cancelled. From the ashes of the Venus Orbiting Imaging Radar arose Magellan, a more economical but still incredibly effective spacecraft that should cost the government something closer to $1 billion in 2020 money. A bargain. To achieve this, several features from VOIR were scrapped, and NASA, specifically JPL, seems to have basically started rooting around their closets looking for spaceship parts they already had lying around. For the high-gain antenna, Magellan used a spare from the Voyager program. The command and data system came from Galileo. The star scanner design came from the inertial upper stage. The gyroscope design came from Viking. The propellant tank design came from the Shuttle Auxiliary Power Unit, and the radio frequency tube assemblies came from Ulysses. And it didn't stop there. Not only did Magellan get a bunch of hand-me-downs from its siblings, it also had to take the long road to Venus in order to make way for the Galileo probe. That one's going to take a moment to explain. Magellan was originally supposed to launch in 1988 using the new Shuttle Centaur system. After the Challenger accident, Magellan lost its launch window and its upper stage. It waited in storage and was redesigned to ride on the inertial upper stage, bumping up the overall cost. And thanks to the delay, the new launch window would place it right on top of the launch window for Galileo, which was being sent off to Jupiter. So instead, the trajectory was tweaked a bit, allowing the April to May launch window that we'll be seeing today. The price was that instead of a 4-month journey to Venus, Magellan would live up to its name and circumnavigate the solar system, doing a full trip around the sun before arriving at Venus 15 months after departing the Earth. I'm sure younger siblings everywhere will relate. We'll talk more about our remarkable payload once we get on orbit, but first let's meet our crew. We'll be flying with a crew of 5, only one of whom is a rookie. When I watch Formula One, one of the things the commentators like to do is come up with esoteric and weirdly specific statistics and trivia. So here's my own version. This is the first American flight with a crew greater than 2, having only one rookie, since Apollo 12. I'm sure that one will come in handy. Commanding STS-30 was Dave Walker, who we last saw flying as pilot on STS-51A. That's the one where Discovery deployed 2 ComSats and retrieved 2 different ComSats, resulting in a well-known photo of mission specialist Dale Gardner holding a for sale sign in front of the rescued spacecraft in the payload bay. This is Walker's second of 4 flights. Next up is our pilot, Ron Grabe. We last saw Grabe flying as pilot of STS-51J, the first flight of Atlantis. This is his second of 4 flights. Moving back in the flight deck, we find our lone rookie for this mission, Mission Specialist 1, Mark Lee. Mark Lee was born on August 14, 1952 in Viroqua, Wisconsin. He earned a bachelor's in civil engineering from the U.S. Air Force Academy and a master's in mechanical engineering from MIT. In between those 2 stints in school, he joined the Air Force, learned how to fly, and spent a few years flying F-4 jets around the world. He was selected as an astronaut in 1984, and this is his first of 4 flights. Riding in the middle of the flight deck was someone we know pretty well at this point, Mission Specialist 2, Norm Thagard. We're familiar with Thagard from his strenuous testing of Skylab equipment back in the 70s, but most recently from his flight aboard STS-51B, operating experiments on Space Lab. This is his third of 5 flights. And last but not least, Mission Specialist 3, Mary Cleave. We last saw Cleave on her first mission, STS-61B, which is most known for its Tinker Toy-like ease and access payloads. This is her second and final flight. The mission was originally scheduled for April 28, 1989, but the launch was scrubbed at T-minus 31 seconds thanks to a short circuit in the liquid hydrogen recirculation pump on engine number 1. STS-30 could only get away with so many scrubs. Remember how I said the planets had aligned for this mission? Well, the way interplanetary departures work is that as the planets move around, a trip from Earth to Venus will take a varying amount of time and energy to complete, depending on the relative positions of the planets. It's good to have a trajectory that minimizes the time of flight, but as we just saw, there are sometimes reasons to choose a longer flight. More important is the amount of energy required. If a probe needs to be kicked away from the Earth faster, it's going to need a bigger rocket, which is going to leave less room on the probe for scientific instruments. So you really want to find a trajectory that, in addition to satisfying your other requirements, uses as little energy as possible. Once you've designed your spacecraft with a specific amount of energy in mind, you've committed to a trajectory that doesn't exceed your energy budget. As the planets move relative to each other, the target trajectory will start to become possible, but only for brief parts of the day. On April 28th, Atlantis had an 18-minute window to get off the pad. That window would grow by about 7 minutes a day until mid-May, when it would reach about 2 hours in duration. Then it would start shrinking again until it finally closed on May 28th, so that was their hard deadline. 6 days after the engine problem, Atlantis was ready to try again. It's a good thing that at this point in the Venus departure window, the launch window was getting longer, because Atlantis was held on the pad for 43 minutes due to excessive cloud coverage and crosswinds at the shuttle landing facility. If Atlantis were forced to execute a return to launch site abort, the weather would have been unacceptable. But the weather eventually cleared up. So on May 4th, 1989, 1 second shy of 2:47 p.m. local time, Atlantis roared off of Launch Complex 39B. The ascent was uneventful, but a bit different from what has become the new normal. Instead of a direct insertion, one that doesn't require an OMS 1 burn immediately after main engine cutoff, this was a standard insertion, the old way. As I understand it, this is because the shuttle used a small amount of yaw steering during the ride uphill to tweak the final orbit and make things a little easier for Magellan. But the cost of doing that is decreased performance, which explains the standard insertion and also why there aren't too many secondary payloads on this flight. Once Atlantis arrived on orbit and performed the OMS 1 and OMS 2 burns, it was time to get to work. The procedures for deploying Magellan would seem pretty familiar to the astronaut crew, as well as to us. That's because with Shuttle Centaur off the table, Magellan's new ride to Venus is the good old inertial upper stage. Yep, the same upper stage that we've been using to kick TDRS after TDRS into geostationary orbit. So the Magellan deploy was really just a carbon copy of a TDRS deploy. The payload bay doors were opened, the payload was tilted partway up in its cradle, a few checks were done, it was tilted to the deployment angle, Atlantis slewed to the deployment attitude, the restraints were released, and America's latest planetary probe was on its way. 40,000 pounds departed the shuttle, with Magellan itself taking up less than 8,000 of those pounds. The tyranny of the rocket equation indeed. At this point, the crew's involvement was pretty much complete. They watched the solar arrays deploy, the pilot crew blipped the OMS engines to move away, and they turned the bottom of the orbiter towards Magellan so the plume from the upper stage wouldn't gunk up the windows. An hour after deployment, the first stage of the IUS ignited, and it was off to Venus. It's a good thing that Magellan was pretty sturdy because it was really moving. Its departure burn to Venus pulled something like 2 Gs, and when it eventually arrived at Venus, it experienced 7 Gs of acceleration during its insertion burn. That is 7 times the strength of Earth's gravity. Thanks to Magellan taking the scenic route, we have 15 months to kill, so let's learn a little more about this Venus-bound spacecraft. As it sat in the payload bay, it was 38 feet tall, with 17 of that being the inertial upper stage and 21 feet being Magellan. That's 5.2 and 6.4 meters for the metric-minded. Its most distinctive feature was a 12-foot wide dish-shaped antenna on top. Below that was an equipment module housing a bunch of computers and electronics and stuff, measuring about 5 by 4 by 3 feet. And below that was the propulsion module, containing a smaller solid rocket motor for entering Venusian orbit and hydrazine-powered thrusters for attitude control and orbit maintenance. Visually, it sort of reminds me of one of those bacteriophage viruses with the spidery legs, the central pillar, and the icosahedron head, aka D20, but with a dish instead of a D20. So, in summary, like basically every scientific spacecraft, Magellan was made out of a bunch of instruments, electronics to support those instruments, computers to parse instructions for those instruments, antennas to send the data from those instruments home, and rockets to move the whole thing around. Those of you who are paying extra close attention or remember your elementary planetary science will realize we have a problem here. I listed a bunch of equipment on Magellan, but at no point did I mention a camera. But even if there was a camera, Venus is completely covered in clouds. How is Magellan going to peek underneath? The answer is actually something we've briefly touched upon before: synthetic aperture radar. Radar, which is actually an acronym for radio detection and ranging, is a technology that sends out a pulse of specialized light, waits for it to bounce off of something, and then receives the reflected signal. By looking at the properties of the returned signal, we can learn about whatever object the pulse bounced off of. And by looking at the time that it took for the reflected signal to come back, we can determine how far away that object is. Sounds like the perfect thing for mapping a planet. And radar is just a different frequency of light. It's like a weird color that we can't see. And light is an interesting thing. If you change the frequency, it will interact with matter in completely different ways. For most office buildings, the windows are transparent to visible light, so you can see through them, but opaque to infrared light, so that the building doesn't become a giant greenhouse. Visible light barely sees the windows, while infrared light bounces right off. The problem we have is that Venus is completely covered in clouds that visible light bounces off of, but that radar goes right through. Specifically, Magellan is using a 2.385 GHz S-band signal to go right through those clouds. What's interesting is that's actually not too far off from the frequency used by a typical microwave oven at home. And what's really interesting is that Magellan's radar is only pumping out about 325 watts of power, while my microwave at home is around 1,000 watts. So we basically sent a fancy, low-powered microwave oven to Venus and left the door off. Hopefully it doesn't pop the planet like a giant popcorn. The synthetic aperture part comes in by taking radar processing up to the next level. I don't fully understand synthetic aperture radar myself, so if anyone has any recommended reading, please send it my way. But as I understand it, SAR uses advanced algorithms to process the returned radar signals to get more information. By factoring in precise timing, the movement of the spacecraft, and complex mathematics, scientists are able to virtually enlarge the size of the radar dish. So instead of a 12-foot radar dish, Magellan could see as if its dish were 3,000 feet across. That's 3 times wider than the Arecibo Radar Observatory in Puerto Rico. You know, the one you've seen in a bunch of movies. Again, the technical details about how this works is sort of eye-watering, but I combined what I did understand with a few analogies I saw into an image that hopefully clarifies things. Imagine a completely dark warehouse full of stuff. Now imagine that you tape a camera and a flashlight sideways on a skateboard, open the camera shutter, and roll the skateboard into the warehouse. You're going to get a pretty confusing image, but if you carefully analyze when each pixel of the camera was triggered, and you know the movement of the skateboard, you should be able to reconstruct the 3D objects inside the warehouse. That's basically what Magellan was doing, but with the surface of Venus instead of a warehouse, and radio transmitters and receivers instead of a flashlight and camera. For each 3-hour and 9-minute long revolution around Venus, Magellan had a regimented schedule of tasks to complete. To start off, it would take about 5 minutes to turn its main dish to be perpendicular to the direction of travel, just like the camera on the skateboard. Next, it would begin a 37-minute-long data acquisition run, bouncing radar signals off of the surface of Venus, tracing out a long swath. After 37 minutes, the swath was complete and the onboard data storage was full. It would then spend another 5 minutes turning to face the Earth. The turns took 5 minutes because they were performed using onboard reaction control wheels in order to conserve fuel. You might wonder why it has to face the Earth at all. Why not just keep its main antenna facing the proper direction for mapping and point its high-gain antenna to the Earth? Well, the mapping antenna and the high-gain antenna were the same antenna. It's that big 12-foot dish. It's clever, but it required a lot of turning back and forth. Once Magellan was facing the Earth, it took a couple of minutes to sync up with the Deep Space Network, and then it spent about an hour relaying half of the data it just collected. The data was relayed at a blistering 270 kilobits per second, roughly equivalent to the old Edge cell phone network. Since there was so much turning going on here, it was important that the spacecraft had a good idea of which way it was facing, so it would take the next 14 minutes to check in on some known stars. This realigned the attitude system and made sure that everything kept pointing where it should. Twice a day at this point in the orbit, Magellan would also do what's known as a momentum unload. We don't have time to get all the way into this, but thanks to the uneven gravity of Venus, the reaction wheels would be forced to spin faster and faster over time to keep Magellan pointed where it wants to go. Spacecraft operators can't just slow the wheels down because then Magellan would turn somewhere else, thanks to the conservation of angular momentum. So what they do is slow the wheels down while carefully firing thrusters to keep the overall spacecraft pointed in the same direction. And this was basically the only time it really needed to expend fuel. After that, it would play back the second half of the data to the DSN and get ready to do it all over again. 7.5 times a day for all 243 days of the Prime mission. As I mentioned, Magellan's Prime mission was 243 days, but it provided such a wealth of data and was in such good health that its mission was extended again and again, eventually extending to nearly 4.5 years. On October 13th, 1994, Magellan's mission came to an end, and it became one with the planet that it had been studying, plummeting into the hazy clouds below. To say that the mission was a success would be an understatement. It mapped out most of the planet's surface with incredible detail and revolutionized our understanding of Venus. And there's even a bunch of other stuff it did that I had to cut for time, but talking about an uncrewed, long-duration mission like this was pretty cool. Next time, with Atlantis back home from its fourth mission... Oh no, we forgot about STS-30. We followed Magellan to Venus and left poor Atlantis stranded in low Earth orbit. Let's wrap up the rest of the mission. When we last saw Atlantis, it was only 7 hours into the flight, having successfully sent Magellan on its way. The mission didn't actually end there, but due to the payload limitations, there wasn't a ton more to cover. A special furnace was operated down in the middeck to attempt to grow big, pure crystals out of a small seed. Mission specialists Lee and Thagard suited up in the extravehicular mobility units, and the pressure in the orbiter was lowered, all to test some new procedures for doing an EVA on the first day of a future flight. Specifically, this was done in order to prepare for the upcoming deployment of the Hubble Space Telescope, which might need a little help getting out of the payload bay. The crew also did their part for the cause of space situational awareness by once again being observed by the Air Force Maui Optical Site in Hawaii. By doing stuff like performing a water dump or blipping the thrusters while being watched, they could help the Air Force calibrate their equipment and better recognize what was happening in space. Specifically with spacecraft that might not be quite as willing as the shuttle to tell the Air Force what they're doing. But after 4 days, blink and you miss it, the mission was already over. The OMS engines fired up, slowing the orbiter down by 100 meters per second, which was all it needed to start the trip home. During the final approach, Commander Walker completed one last test, assessing the orbiter's performance during a 12-knot crosswind landing. Crosswind landings were generally avoided, but since they might not always have that option, it was best to know how the shuttle handled them. 4 days, 56 minutes, and 27 seconds after lifting off, Atlantis touched down at Edwards Air Force Base, one interplanetary probe lighter. Next time we're actually going to do something a little different. If you include stuff like the supplementals or my appendicitis message, we passed this milestone a little bit ago. But the next episode will be the 100th proper episode of The Space Above Us. And since imitating history podcaster Mike Duncan is what got me into this mess in the first place, I figured that I'd follow in his footsteps once again and celebrate my 100th episode with a Q&A special. If you've ever had any questions you wanted answered on the show, now is the time to send them in. They can be about old space stuff, current space stuff, future space stuff, fictional space stuff, podcast stuff, personal stuff about me to an extent, and unrelated stuff like movies, video games, or whatever. Send your questions in either via email to jp@thespaceabove.us or via Twitter where I'm @spaceaboveus. The cutoff will be sometime around February 3rd, 2020, but if I don't read your question on the podcast, I'll be sure to answer it directly. Also, I plan on reading people's first names, so if you don't want me to do that, or you want me to call you something else, please let me know. Send in some questions, and let's have some fun. Ad Astra, catch you on the next pass.